Well, I'm very pleased to be here. I'll be with you guys, a captive audience. I've never had an audience that can't leave before. So that's a heck of a feature. You guys should advertise that. And we're going to talk for the next hour and 45 minutes about this topic, engineered nanoparticles and health, sorting through the hype and rhetoric. Okay? Now, my background is I'm originally an industrial hygienist, okay? And for the last almost 8 years now, I've worked at the Lawrence Berkeley National Laboratory as the facility and EH&S manager for this division, the Materials Sciences Division. And a lot of different groups do nanotechnology research at LBL, but probably 2/3 of it does come out of our division. So we have about 1,000 people in our division that I interact with, and a goodly chunk of those people are involved day in and day out in terms of making nanoparticles, studying nanoparticles, doing different kinds of things related to nanotechnology. So I got involved very early in this field. Back in the early 2000s, the Department of Energy, which actually funds the Lawrence Berkeley National Laboratory for the most part, the Department of Energy funded 5 regional nanotechnology user facilities, including one in Berkeley, Molecular Foundry. And what these are is staffed labs with expert scientists and state-of-the-art equipment that anybody can use if they can submit a proposal and get it accepted. And it's free for most people, unless you're a private company and your proprietary data you're collecting. For everybody else that's willing to publish their data, it's free. The government pays the expenses of the lab time and the supplies and the researchers and stuff like that. So we get people from all around the world come there to do nanotechnology research. It's about a 100,000 square foot building just dedicated for that purpose. And that's only a fraction of the kind of nanotechnology stuff we deal with. So I've been immersed in this milieu of nanotechnology and health now for almost 8 years. So to me, it all kind of seems old hat. But the truth is, for a lot of people, this is still a pretty new topic. Okay, and as this becomes more and more prevalent in industry and research facilities and stuff like that, more and more people are going to have to deal with this issue. So a couple of times, we've had students graduate from LBL because we're part of the University of California. We have students graduate, and they go out and find jobs in corporations. And then they're calling me 6 months later and said, we need to talk because we're doing a bunch of work with nanoparticles, and I'm not sure we know what we're doing. So I'm always glad to go do those things and give people a presentation to give them a little bit of grounding. So that's what I want to do for you guys here. And like anything else, there's always a lot of hype involved with new stuff, especially where there's potential for large quantities of money involved. And so there's been a fair amount of hype, both in terms of what nanoparticles might do for us in the future and in terms of the potential health effects. And like anything else, we'll talk about the hype cycle later on. Like anything else, you have to sort of temper the most extreme statements that you read in any regard. And we're going to talk a lot about that as we go through this. So if there's any questions as I speak, just go ahead and raise your hand. And as long as I can stay pretty much on schedule, I'll try to answer your questions and maybe address your issues. So, all right, let me get up to my computer here. So it turns out that pretty much my whole career had to do with particulate matter. So recall, I originally started as an industrial hygienist. And so industrial hygienists, if you don't know, are people that are trained to deal primarily with chemical hazards, but also other stuff like physical hazards and radiation hazards. But one of our biggest things is chemical hazards. And it turns out, just by luck or whatever, my career has been pretty much centered on particulate matter. So out of graduate school, my first job was at Mare Island Naval Shipyard in Vallejo, California. And I worked for an organization called Code 106. Code 106 came into being pursuant to a 60-minute television segment where 60 Minutes strongly criticized the Navy for failing to control asbestos exposures of the shipyard workers. And in fact, it was so... Admiral Rickover, who was in charge of the Navy at that time, was so incensed that he invented the Code 106, originally called 100X, across all the Navy shipyards to put safety and health people in a line management type position rather than purely as off-to-the-side staff that visits now and again. And so asbestos was one of the major emphases at the very beginning of my career, and later on, when I worked for the university, I got an EPA grant. We set up the first asbestos training center west of the Mississippi. It shows you how old I am back in the day. But since then, it seems like everywhere I go, I'm either dealing with silica or lead, beryllium, Beryllium was a really big issue when I worked at Lawrence Livermore National Lab. And in general, beryllium was a big issue across the DOE complex because they had effectively poisoned thousands of people by beryllium exposure. And some significant subfraction of those people became sick, and some smaller fraction of those people died due to beryllium exposure. I knew one guy I had met that actually died at Livermore when I was there. And I met a bunch of people that were disabled by that exposure. Just like when I worked for the Navy, I met a bunch of guys that were disabled because of the asbestos exposure. Very impressive to me as a brand new, impressionable young kid to meet these guys that really couldn't do anything but sit at a desk anymore because their lungs were so damaged by the materials they'd been exposed to. Anyway, so nanotechnology is just sort of along those same lines in my career. So for the last 8 years, this has been one of the main issues that I deal with up at the Lawrence Berkeley National Lab. So we have things like nanoflowers, which are complex nanocrystals, nano deposition and nano machining. So these things are done on the nanoscale. We'll talk about what nanoscale means in just a little bit. Individual nanoparticles, which are the main thing I'm going to talk about today, are these individual nanoparticles. If you can see this picture right here, you see those little dots on that picture? Those are actually individual atoms in that nanoparticle. Strictly speaking, they're columns of atoms, but as the microscopists will always tell me, but they are basically atom scale. So you're seeing the connections in the holes between the atoms in that picture. And so this nanoparticle, the whole thing across, is only about 5 nanometers. Okay, so a remarkable thing. Nanobombas, lots of different nano things. So in the world of nanotechnology, there's a lot of stuff. We're going to be mostly talking about the nanoparticles, though, because that's where the health concern is. So just what is nanotechnology? And I'll tell you right off the bat, there are many, many definitions of what is nanotechnology, and not one of them is anywhere near satisfactory. So I work with all these high-level scientists at a premier research institution, and any definition you'll throw at them, they'll find 50 examples that don't fit the definition. So I no longer try. Madness lies that way. It's kind of like the Supreme Court decision on pornography. Well, we can't define it, but we know it when we see it. All right? That is the Supreme Court decision. Well, what we're talking about are things that are extremely small. This is a little bit of a crowded graphic. Do I have a laser pointer? Is there not equipped with a laser pointer? Okay. So we're talking about things that are very small. If you start at the top of this scale here, you're talking at the centimeter range, so those are things like this big. And you go down orders of magnitude and you get into the microscopic world. And if you keep going down and down and down until you get to nominally 100 nanometers in scale, okay, then you're into the nano world. Now that's totally arbitrary, and I like to think really maybe one order of magnitude above there. We should think at least as kind of nano, but the most people, when they say nanoparticle, they're referring to a particle that has at least one dimension that's less than 100 nanometers. Okay, now they can have other dimensions that are much longer than 100 nanometers or much bigger, but at least one dimension that's 100 nanometers or less, basically down to about 1 nanometer. And when you go below 1 nanometer, you know, they're not really particles anymore. They start turning into gases and vapors. Question?
Can you give us a little bit of perspective on what a nanometer is?
So a nanometer is, there's a micrometer. That's a millionth of a meter, so a meter and 1 millionth of that. So if you chop a meter into a million pieces, that's a micrometer. If you chop it down again by a factor of thousands, then that's a nanometer. Okay, so we're talking about 100 nanometers is the best optical microscopes in the world. Okay, $10,000 for a Nikon microscope, optical microscope, cannot see nanoparticles. Okay, they're sub-microscopic, hence not in the micro world. They're in the nano world. You have to have electron microscopy or one of the other tools to see nanoparticles because they're so small. So we're talking about things that are extremely, extremely, extremely small by the standards that most people have in their life. Okay, is that a good answer? Okay. Yep. Now, a little bit of folklore review. So many people trace the beginnings of nanotechnology to a speech given by the famous physicist from Caltech, Richard Feynman, back in 1959. He gave a speech, the title of which is pretty famous now, There's Plenty of Room at the Bottom. Okay, and he was talking about the possible kind of things that can be done if you can work on the nanoscale. Now, Feynman was an uber character. My favorite book of all time was his book called Surely You're Joking, Mr. Feineman. And so he's a funny guy, but he gave this presentation, and people that think about this go back and say that was the beginning, because somebody actually threw down the gauntlet of doing this kind of work. What I want to talk about is the problem of manipulating and controlling things on a small scale. Why cannot we, for example, write the entire 24 volumes of the Encyclopedia Britannica on the head of a pin? So he was, people in those days, 50s, were thinking big, right? He said, well, there's an alternative. Think really small. So here's the Bible on the head of the pin. Okay, so that's pretty routine. The word nanotechnology was started to use more in the 80s, and there was this author / popularist / I don't know what he was really, Eric Drexler, and he published a book called Engines of Creation, The Coming Era of Nanotechnology, which was one of the first sort of public airing of the use of the term nanotechnology, and it stuck pretty good. He was predicting gay goo from unchecked reproduction of self-replicating robots. Okay, so that's not actually our concern at this point. We don't have any risk of self-replicating military robots just yet. The issues are a little more basic than that at this point as we go forward. So there's two things you can do in nanotechnology. One is to end up with a nanoscale thing. One is you can take a bigger something and grind it or etch it down to a nanoscale something. So now all CPUs and computers, they have circuits on the nanoscale. Okay, what are we down to? 45 nanometers now, and they keep getting smaller and smaller. That's an example of making a nanoscale features on a surface by taking a big thing and grinding it down to the features you want. The other alternative is to build something up from essentially atoms, one atom at a time. And that's called bottoms up, and machining is top down. Okay, so you take something big and you basically make it into the nanoscale you want, or you take basically individual atoms and make it into a nanoscale object that you want. So these are two sort of the two big approaches to nanotechnology. Now it turns out none of this would have been very interesting, or actually probably would have received as much attention, except for the fact that there were significant advances in your ability to see nanoparticles back in the 80s in particular. So when Feynman gave his speech in 1959, the resolution of the best transmission electron microscopes was 10 nanometers. Okay. Now, anytime I want to walk a couple of floors down to the building I live in, I can walk in on the electron microscopist using an off-the-shelf commercial instrument whose imaging at least 10 times better, and you can see the individual atoms in the material that they're looking at. So there's been at least a tenfold. Now, I also am involved with the National Center for Electron Microscopy, which has the highest resolution TEMs in the world, where you can see the bonds between atoms in those facilities. There's some other devices that have been developed, the STM, scanning tunneling microscope, and the atomic force microscope, that again, these now give us the ability to actually image at the nanoscale that didn't exist before this era here. So the ability to actually see what you've got has contributed a lot and actually made the nanotechnology thing possible. Here's the famous 1989 IBM advertisement where these two scientists, Eigler and Schweitzer, moved xenon atoms into place using a scanning tunneling microscope to spell out IBM. So each one of those peaks corresponds to a single xenon atom. Okay, example of bottom-up nanotechnology. So there have been 2 Nobel Prizes so far. Of course, where I work, the gold standard is Nobel Prize. We've had 2 in the last 4 years, and a long history of many Nobel Prizes before that. There have been 2 for nanotechnology so far. The buckyball, which is a C60 spherical molecule named Bucky after Buckminster Fullerene, who was a champion of geodesic domes. And this is essentially a geodesic dome on the nanoscale. A standard 60-carbon buckyball is 1 nanometer across and really sits at the bottom end of the nanoscale, if you think about it. So there's a Nobel Prize for that in 1996, I guess it was. Or maybe it was a little bit later. I think it was 96, yeah. And then just a couple of years ago, we got the Nobel Prize for graphene, which is another carbon nanoscale material that can be big and flat, but very nanoscale thick, including as thin as 1 layer of carbon atoms. So these are 2 brand new forms of carbon that nobody knew about before this research. And so The old forms, graphite, diamond, and stuff like that, have some new brothers in what are called allotropes of carbon. In fact, I just mentioned that buckyballs, this discovery was out of University of Texas, so buckyballs are, in fact, the state molecule of Texas. Okay. It's probably good that they're black gold. Texas N, nanoparticles. The other thing that's true is people are making nanoparticles out of almost everything on the periodic table. This is a slide I got from University of New Mexico. I can't remember if it was exactly what it was, but this is one laboratory in one university. And this shows the diversity of chemistry they're using to make all these different nanoparticles. So now you can begin to get the idea that there's a lot of things people are making that we have to ask questions about. What will it do when it's released into the environment? What will happen if it's injected into you for medical purposes? What will happen if you breathe it in a factory making tennis rackets? Okay? Tremendous diversity of materials out there. This is one lab. The whole nanotechnology revolution is going to impact everybody eventually, but right now it's really impacting the sciences and medicine. They have plans. They've shown that you can use nanoscale things to enclose drugs and get those nanoscale things inside of cells where the cell pops them open and releases the drug only inside of the cell. Things like that. Chemistry, physics, energy. So, one of the big emphasis where I work now is battery research. That, of course, if we could come up with better batteries, there'd be a lot of good things happening. And a lot of that research on materials that go into batteries is at the nanoscale these days. So we're involved in quite a bit of that. So just all sorts of stuff. Energy, hydrogen storage. We'd like to have this hydrogen economy, but you got to have a way to store it in a solid state because you really don't want compressed hydrogen in every car. And this is all the kind of research that our guys are involved in. We deal primarily with energy research, and so much of it is at the nanoscale. Environmental remediation using nanoparticles. So you're going to release engineered nanoparticles in the environment to take care of other kinds of problems. And you've got to hope that the materials you release don't cause a problem that you're not aware of. Let's spend a couple minutes talking about one of the best characterized nanoparticles out there, and that's the carbon nanotube. Now remember the buckyball. So the buckyball is a sphere of 60 carbon atoms, arranged just like a soccer ball, essentially. Okay. Now if you take that sphere and start pulling it apart and starting adding carbon atoms in the middle, you start getting a long chain. And this eventually develops into a carbon nanotube. Now they come in two varieties, though I realize this picture is wrong. Later I have a better picture. They come in two varieties. They come as independent carbon nanotubes, one layer, essentially one round layer of atoms. Okay? And they come as multi-wall carbon tubes, one layer inside of another, like those Russian dolls. Okay? So we have two forms of carbon nanotubes. So in terms of hype, in terms of toxicology research, in terms of short-term applications, carbon nanotubes are way at the top. In terms of potential miracles, carbon nanotubes are way at the top. So there's been a lot of attention paid to them. So here are some of the things. These are American Scientist, Nature, different magazines. This is nanotubes as chemical probes, nanotubes as quantum wires, nanotube membranes. That's actually a near-term field. Here's one I like. A space ladder made out of a carbon nanotube rope. Space ladder, the concept is it's theoretically possible that if you can tether something to the ground and put a counterweight in orbit, instead of blasting into orbit, you can just climb the rope. Okay, much more energy efficient. But no material has ever been developed that is light enough and strong enough to do that. Theoretically, carbon nanotubes are light enough and strong enough to do that if they can produce them in that form. So there's a whole lot of potential things: stronger than steel, lighter than aluminum, more conductive than copper, except when they're not, when they're a semiconductor, more powerful than a speeding locomotive. That may not be true, but everything else is part of the hype on carbon nanotubes. You can buy these things on cheaptubes.com, okay? And CheapTubes is going to come up again later, so remember that name, cheaptubes.com. You can log on and you can order up some carbon nanotubes. Here's some electron micrographs of a single-wall carbon nanotube. And here's an electron micrograph through the side of a multi-wall carbon nanotube. That's a drawing at the end showing you the multi-layer structure inside of it. It's got 2 layers, 3 layers, 4 layers, 5 layers. And so therefore they can get pretty big in diameter because the little one grows a bigger one, and bigger one, and bigger one on side. Whereas these are typically on the order of 1 nanometer across. They're very, very small, the single-wall carbon nanotubes. Of course, in the real world, they're complicated messes like this. A lot of these little particles you see here, those are contaminating catalysts that were used to make the material. So those little round things you see over there are really just other carbonaceous crap that you get when you make these things. So typically straight from the factory, they're not very pure, although that's improving. And we'll talk about how that screwed up the toxicology research in just a couple of minutes. I mentioned earlier the hype cycle. So this is a generic concept for anything new, where people think that it's going to be the next big thing. People want people to invest money in it, and everybody thinks this could go big. The hype cycle, the graphic down here, and I actually took that from the Wikipedia entry on hype cycle. Okay, so when some new technology is announced and looks promising, everybody gets very excited. This leads to the peak of inflated expectations, where the whole world is going to change, it's going to happen tomorrow, and we're all going to be millionaires. Okay. And over time, there's usually some problems that crop up, like the nanotubes. Man, they had a big hype cycle, but then it became pretty darn clear that they're very toxic. Okay, and all of a sudden, well, probably we can't use them for everything we were going to use them for, because it turns out if you inhale these, they're pretty toxic. So then you get into the trough of disillusionment, where you say, oh, God, I invested all that money, I'm not going to make any money. And you start thinking maybe this isn't going to pan out. As is often the case with these things, it's somewhere in the middle, right? And then you eventually go up the slope of enlightenment and the plateau of productivity, where these materials are being used on a regular basis. And these things are getting a lot of use out there, both in consumer products and in high-tech stuff. One of our students went to a company that does a lot of government military fabrication and stuff like that. They're very interested in carbon nanotubes because they have some very interesting properties that might be useful to the military. So we are now, for carbon nanotubes, we are pretty close, I think, to the top of the slope of enlightenment, or at least well up the slope of enlightenment toward the plateau of productivity as we go along. This is a curve showing production capacity announced for carbon nanotubes and what they expect the growth curve going to be in terms of use of carbon nanotubes. Now, will that really happen? You know, it's like any other projection. We'll have to wait and see. So, we talked about nanoparticles as having some concerns. So what are the issues with engineered nanoparticles? Note I used the term engineered nanoparticles, or ENP for short. That means nanoparticles that have been intentionally designed to be the way they are. In other words, not accidentally. We'll talk about accidental nanoparticles later on. So what are the concerns? Why are we worried? What has been shown about the toxicity of engineered nanoparticles? How can we control people's exposure to engineered nanoparticles? Here's a very early nanotechnologist. His duty was shrinking kids. So when we talk about engineered nanoparticles, things intentionally made the way they are. What we're really concerned about are unbound engineered nanoparticles, not firmly attached to a surface. A lot of nanoparticles are growing on the surface. As long as they stay on the surface, they're not a problem. But once they get released from that surface, then they can be inhaled, they can be released into the environment, they can go out in the trash, they can make it into the bay. That's what you have to worry about. Not part of a bigger item, such as microchip or cell wall. This is a big issue. One of the hardest things to define are, really big biological molecules like protein are nanoscale molecules. And so do they fit into this or not? That's part of the reason I don't even try to describe or define nanotechnology anymore. We're talking about particulate matter that can become airborne. This is a picture of a small scale-up factory making carbon nanotubes. And you can't maybe see it so much on screen, but there's a cloud of dust there. Okay? And so those workers wearing those disposable dust masks and 2 layers of gloves and stuff are potentially exposed to these carbon nanotube materials of uncertain toxicity. So that's what we're worried about. We're not worried about this book published in, I think it was 2002, military nanobots run amok and reproducing themselves and killing and all that stuff. That may happen someday, but that's not the issue right now. We're talking about basic environmental toxicology and occupational toxicology and potential impact on consumers as well. So there's two slightly different issues here. One is going from a microscale particle to a nanoscale particle. The toxicity that you normally see associated with a microscale particle might get worse as the particles get smaller. In other words, a single gram of material that's this much toxic in the microscale might be this much toxic for the same material once you grind it down to the nanoscale. That's one concern. Okay. The second concern is as you go from the microscale to the nanoscale, entirely new toxicities show up that didn't exist otherwise. Both of these are true to some extent. Okay, and we'll see examples of that. So there's the enhancement of the sort of ordinary expected toxicity, and then there's the absolutely new out of the blue toxicity. And we'll see examples of both. People have been burned before, of course. They have these great graphics from the 30s and stuff on how lead is great for your health. And it might have been true in those days, I don't know. But if you ever read the story of tetraethyl lead in gasoline, you wouldn't believe anything they say. MTBE in gasoline, amazing asbestos, floss your teeth with it. So people have been burned before, and the question is, are we going to add nano to that list going forward? The other thing to consider is that nanotechnology is not all new. So here are some stained glass windows from Europe, and it turns out to get some of these colors, they would use nanoscale gold and nanoscale silver. And the artisans of the day knew how to fume those materials, so they arrived in different nano sizes, and the different nano sizes impart different colors. Okay, so not everything about this is new. This is a carbon black factory, and you can see maybe scale. This is a guy here. Okay, so these are gigantic vats making carbon black in massive quantities. Carbon black is a nanoscale material, and to some extent it's engineered. And so that ain't new. They've been doing that for over 100 years. Fumed silica, iron oxide, titanium dioxide, nanoclays. A lot of these things are on the market and have been for many years. So sometimes people will act like this is totally new. It's not totally new. And of course, a lot of nanoparticles are not engineered. Here's a guy welding. And when you weld, you create billions of nanoscale particles. Okay, especially if you're like this guy and you got your face right into welding. These little ones are nanoscale spheres of the metal. Question?
I'm sorry, I know that you don't want to define nanotechnology, but nanoscale particles and molecules seem to me to be maybe the same thing. What's the difference?
Yeah, the answer is you're right.
Molecule?
The answer is you're right. At some point, nanoscale particles and molecules are the same thing, and there isn't a difference. So we talked about biological molecules. A protein is a nanoscale thing, and it's also a molecule. A buckyball, by most accounts, is a molecule, but it's also a nanoscale particle. So there is no clear distinction. That's the reason it's so hard to define this kind of thing. So that's the truth.
How come you're calling the welding fumes nanoparticles rather than exhaust or something like that?
Well, if you collect, they are particulate matter. So if you run them through a filter, and you can collect them on a filter, and you can look them under an electron microscope. Okay, and in a sense, they are molecules too. They're depending upon the crystalline structure, they're molecules too. But generally regarded as a nanoparticle because it's solid. You can see it under an electron microscope, and that's also true for a biological molecule. And we don't really call those nanoparticles. So the truth is, that's why I don't even try to define it.
I'm sorry.
We had a question up front somewhere?
I was just going to say the structure might be different than what you would have naturally occurring.
So all kinds of people, every diesel truck that goes by creates billions and billions of nanoparticles. In fact, we used to have these terrible diesel buses at LBL. When I'd be in a lab monitoring for nanoparticles, you can get these big peaks just in the background. Now it's because the bus went by 2 minutes before. This is actually a picture of carbonaceous nanoparticles from the exhaust from a diesel truck. Okay, so we talk about environmental justice on these places where like the Port of Oakland. So it's in a otherwise not very affluent area, and thousands of trucks are going in there, and they're spewing forth this stuff on these relatively economically disadvantaged people, and that's where we get this sort of concept of environmental justice, that sort of thing. What are the risks? So why do we have any a priori reasons to be concerned? Do we have other examples where size and nanoscale matters? And the answer is we sure do. Okay, so at the top you see some of the fellow suffering from asbestos. Like I said, when I came out of graduate school and went to work at Mare Island, I met these guys that were disabled because they had been exposed to asbestos. And the same guy said, oh yeah, I'm just disabled. My friend, he's dead. Okay, so that was pretty impressive to a 26-year-old kid coming out of graduate school. It turns out that the chemistry, the molecules, if you will, that make up, in this case, let's take a look at chrysotile asbestos, one variety. They come in multiple forms. In a non-fibrous form, that doesn't have those little fibers. It's called the state rock of California. Okay, same chemistry, different arrangement of atoms in the same chemistry, and you have serpentine, the state rock of California. Now, if you just happen to have a deposit where it morphed at just the right rate and all the nice things were in place, like we have lots of in California, that crystalline structure changes, and you get the crystalline structure of chrysotile asbestos. Now, it turns out the state rock of California is not particularly hazardous at all. The asbestiform, in other words, asbestos-shaped variety of the same elemental composition, is very dangerous. There's a great BLM land in central California called, I can't remember even what it's called now, but there's this great BLM area that I really want to go to with my telescope. North of there.
Knoxville?
No, it's a big BLM area that's all closed because there's so much asbestos in the soil. Clear Creek. They won't let anybody in now because of the asbestos in the soil. But the point of this is, it is the shape and the size of the particles in asbestos that makes them toxic. Not so much, for the most part, not the chemistry. Okay, it's not 100% true, but it's mostly true. So, and these asbestos, chrysotile asbestos in particular, when you're breathing these in, almost all of them are nanoparticles. Okay, which means if you look at them under the ordinary microscope, like OSHA does, you only see 3 or 4% of the particles. You don't see the other 95, 96, 97% because they're too small, even for the best optical microscope in the world. You have to go to electron microscopy for the most part to be able to see those particles. So we already know that, well, you go from one form to another and you go to the nanoscale, and all of a sudden we see this sort of toxicity. And it turns out it's kind of a robust phenomenon. We'll mention a little bit later on. So that picture down there is an X-radiograph of a person with silicosis of the lungs. So they have breathed in too much, probably quartz, either from working in a mine or jackhammering on the highway or working on building demolition or construction. And they breathe in too much quartz. So it turns out quartz, now when it occurs on the beach, when I go to the beach and lay on the beach, those particles are so big that if you accidentally inhale one, you gag it out, or your lungs efficiently remove it, and nothing bad happens. You take those same particles, exact same sand, and grind it down and grind it down and grind it down into the microscale. Okay? Now, when you breathe it in, your lungs are unable to deal with it. Okay? And it results in chronic inflammation and eventually scarring of the lungs, which is what you see, all that white stuff on the lung fields, that's all scarring of the lungs called silicosis, and cancer. Same exact chemistry, no change at all. So if you're a sandblaster and you shovel some sand into it, there's no hazard when you're shoveling the sand, it's big particles. But when you blast it and it bounces off or whatever it is, a certain amount of that breaks down to the nanoscale, or microscale and nanoscale. And that's the material that causes the toxicity. And then, it's a serious event. There's many people that have been made sick by exposure to silicon. It's kind of a little bit of a soapbox issue for me because outside of big organizations, there's absolutely no control of anybody's exposure to silica. You can go to any sort of little construction thing going on, and there'll be in clouds of silica that I can predict by my industrial hygiene background are 30 times the safe exposure level, and it happens every single day in the state of California. Recently, I saw this happening on a sidewalk thing, and I went over and I told the guys, this is very dangerous what you're doing. You're breathing in all this the silica dust. And they said, well, that's why I'm wearing the face shield. So I left. Okay. There's another example of size-dependent toxicity. And this is air pollution. Now, the example I use down here is an old one, but we'll talk about it in a new context too. This is the famous London fog of 1952. And there was a lot of coal being used in London at that point, and there was a massive inversion, and there were huge concentrations of fine and ultrafine particles being accumulated in the atmosphere. So they're called pea supers. Really, there's kind of a picture down there you can't see down the street because of the pollution. And nobody thought it was that big of a deal because they've had pollution inversions before in London. But when they were done with this incredibly bad inversion, they went around the countryside and they added up the death toll. And depending upon who you read, 4,000 to 12,000 people died because of that pollution crisis. Okay? And since then, it's become pretty apparent. If you could see this slide, these are online for you guys to download. These are, on any given day, the concentrations or actually the surface area, which is another way to measure it, of small particles. And this is the number of people that died. The high end of the graph is 80 to 100 people dying a day. And that's just in selected areas, too. Now, it turns out, remember they talked a lot about the air pollution in China? I got the numbers from China. I got the numbers from London. I did a little bit of conversion factor. China was very close. Okay, so China was very close to the London fog. So undoubtedly, many people have died in China because of this air pollution crisis. We'll probably never know that, but that's the case because it's pretty much what happens when people are exposed to particulate matter and the small scale. Now we know it's really the fine particles, the very fine, ultrafine, I guess, in environmental speak, that are the major source of this excess cardiovascular and respiratory tract illness. And actually, the illness goes on for a fair amount of weeks after the exposure. So people are still dying at an accelerated rate a fair amount of weeks after this particular air pollution event. I lived through a famous air pollution event once where they said 12 to 15 excess people died, and it was bad.
So how does that then factor in duration of exposure as opposed to just concentration and the excess mortality?
Yeah, I don't know if I can answer that question in terms of duration. Like anything else, time and concentration are what affects you. So the longer the time, the higher the concentration. I think this air pollution crisis lasted just shy of a week.
In London?
In London, yeah.
And how about in China?
Well, I mean, that was reported in the news for several weeks. And now they're actually allowing the U.S. consulate to put out data, which they never allowed to do them before, put out ultrafine particle data, or PM 2.5 data. They never allowed that before, so now I can do some conversions to what was measured in terms of total particulate. There's a fudge factor you throw in there and you hope for the best. And you get, actually the numbers are pretty close. Pretty bad stuff. So there's all these examples of size-dependent toxicology phenomena. And here's another one. So not so much now, but in the recent past, there's a lot of people getting artificial joints. My wife actually has 2 artificial knees installed last year. And people that got artificial hips for a while were using a couple of products that were so-called hard metal. So basically hard steel with cobalt, chromium, molybdenum. And this is an example of an artificial hip. You can see one part fits into the other. They're very nicely machined. Well, the problem is, it turns out, say the thousands of people that have been made ill by this, that this hard metal wears away to form nanoparticles 30 to 100 nanometers in size of these kinds of materials. Those result in persistent tissue inflammation, bone loss, joint failure, in a few cases, systemic cardiovascular and neurotoxicity from the wear products on your artificial hip. Okay, so now the main bad actors in this are being sued out of existence now, all that stuff like that. But here's an example where people are suffering now in large numbers due to exposure to nanoparticles from their artificial hip. So what about other people? How are other people going to be exposed? Well, it's pretty clear that there's going to be a whole cascade of people potentially exposed to nanoparticles. Starting with the raw material production and the consumer product manufacturing, that's the worker exposure. Consumer exposure, so I don't know about most, but many of the sunscreens you put on yourself contain zinc or titanium dioxide, okay, nanoparticles. So the people being exposed there's going to be industrial emissions from the factories. Stuff is going to go to landfill at end of life. Some of it's going to go to incinerators. And there's going to be some exposure to the general population down the line. They want to put carbon nanotubes in car tires. Okay, it turns out to be great, except that, as your tires wear away, you're releasing carbon nanotubes into the environment. So it's pretty clear that people are going to be exposed. Cosmetics, that's a big area for nanoparticles now. And there's all sorts of products out there that already have nanoparticles in them. Nanobats. Actually, at the tail end of my son's Little League career, he said, "Dad, they have a carbon nanotube bat. I want one of those now." I said, "You want a $250 bat? Your scandium aluminum alloy is not enough?" So he didn't get his bat. Okay, and he only played one more year anyway. So, washing machines that release silver nanoparticles, okay, that are supposed to be essentially that kill bacteria and things like that. This is a big deal with the EPA. We'll talk about that later on. Nano filters in cigarettes, just like they used to put asbestos filters in cigarettes. Tennis rackets, bicycles, shirts. These are dog bowls that release nano silver so your dog gets nice fresh water. These are food containers that release nano silver so your food stays fresh in there. Goodness knows what happens to you. Baby binky with embedded nanoparticles? Question.
What about a humidifier that uses silver technology for water?
I haven't heard about that, but I would not be surprised if humidifiers use that technology too.
They do.
Is that right? You know, this is all, we'll talk about that a little bit later on when we talk about FRIFRA and EPA regulation of those kind of things. Paint, titanium dioxide, a teddy bear. My favorite, socks that you can wear for a week and then your spouse can sniff them and there's no problem. I told my wife we need some of these, for sniffing purposes. You can buy health foods with embedded nanoparticles. This guy was drinking a lot of nanosilver, in addition to doing other things with nanosilver. And he actually turned blue. There's a clinical name for this. I forget exactly what it's called, but this guy actually turned blue because of his excessive use of topical and ingested silver products. Some people think this guy went too far with his advocacy of nano. No doubt this guy went too far, though. That guy definitely went too far. Now, of course, a lot of people don't like this. They see this as potentially very bad. And so there's lots of people that are protesting, say no to Nanotech. Some people there that took over a conference. Nanotech, it's not big, it's not clear. A website where you can pick your sunscreen, and one of the selection criteria is no nanoparticles. And it'll spew forth the commercial products that don't have nanoparticles. So you can buy one of those. This is my favorite up here, however. This is a group called Thong. Topless Humans Organized for Natural Genetics. And they protest by going around topless. Okay? And if you study the backs of these women very carefully, as I have, what they've written on their back is there's plenty of room at this bottom, okay? And that's a reference to the original Feynman speech back in 1959. There's plenty of room at the bottom. So, protests, different kinds of protests people have. Here's the reason one of the reasons it's going to be possible. Not only do we have spectacular range of chemistries involved in nanoparticles, we have a spectacular range of morphology, shape. And shape matters, as we've seen in the case of asbestos. Here, these are all nanoscale zinc materials. A hoop, a rod, filaments, a forest, whatever you want to call these things, hexagonal things down here. Those are all nano zinc, so they're all the same chemistry. But it's very possible that given them, depending upon the shape, they have different toxicology profiles. All these things matter. Size, shape, chemistry, crystalline structure, water solubility, surface area, surface coating, blah, 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 down the line. So you test your one nano zinc. It may have absolutely nothing to do with the nano zinc the guy's making over there. Which means it's very difficult to get a handle on what sort of environmental and health effect these kind of materials can have. We saw this slide, very broad range of chemistries. Now, it was about 9-10 years ago that real research in nanotechnology, toxicology got rolling, okay? And it should be studied by, I'm not sure what sort of social scientist, but somebody should study it because just to look at the huge number of mistakes that were made in the early research projects that basically invalidated the research project. Over and over again, these things were getting published. That when you found out some detail of it, you say, oh, this is garbage, and you throw it away. Okay, and this happened for several years. This was kind of almost the norm. It was very interesting from a social science perspective. One test that a lot of people are using, it's an in vitro test called the MTT test. It's a measure of mitochondrial toxicity. And basically on this sort of graphic, wherever it's not red, indicates that the cells are not working and they're dying. Okay, so they did this test early on with carbon nanotubes, and there was a lot of cells that weren't turning red. Said, oh, this stuff is really cytotoxic, it's really bad. Turns out the carbon nanotubes directly interfere with the MTT test and invalidate it. Okay, at least as being handled. So all those publications, and there were many of them, round file, round file, round file. Okay, then this is one of my favorites. So they had done a bunch of instillation studies where they would instill carbon nanotubes into the lungs of rats and look for health effects. And that's fine as far as it goes, but it ain't the same as an inhalation study, right, where you actually let the animal breathe it in. So everybody's waiting with bated breath for the first inhalation studies to come out. So this one came out of Albuquerque. I forget the name of the organization. It's a big medical center down in Albuquerque. And they said, well, carbon nanotubes, we study these things, and really we don't see any problem like that. And they had put this picture in an article. This is a representative picture of our carbon nanotube. What's the only problem? That ain't a carbon nanotube. Okay, that's an entirely different species of nanoproduct. So what shows you the researcher looking at the pictures under the microscope didn't have the slightest idea what a carbon nanotube looked like. Okay, round foul right away. Okay, now he got these carbon nanotubes from cheaptubes.com. turns out. So there's a lot of garbage research early on in this process. There's another one I'll show later on where they injected into the rat's lungs and a whole bunch of rats died. And they said, oh, it's really bad. They choked the rats to death. So what are the drivers of nanotoxicity? So we have three different things actually. So this is important. We have three different semi-independent drivers of potential toxicity of nanoparticles. The first one is the intrinsic elemental toxicity. So we do a lot of work with quantum dots, and quantum dots are typically made out of things that are intrinsically toxic, like cadmium. Okay? So if you get cadmium, whether it's nano or not, if you get that into your body, it's going to cause bad stuff. So these particles are intrinsically going to be toxic just because they're made out of toxic stuff. Okay? Lead, cadmium, fluoride, things like that. Let's skip to the third one, morphology-driven toxicity. We've already seen that you can take the state rock of California, which is exactly the same chemically as chrysotile asbestos, and they have extremely divergent toxicity profiles. Okay? So shape-driven toxicity could make a big difference, especially with respect to fibers, but also other shapes maybe too. Okay? And then in the middle, this is a little bit new concept for a lot of people, is surface area-driven toxicity. And I'll show some good slides on this. What this means is that it may not matter how many grams of material you're being exposed to, how many grams or milligrams of material you're inhaling. What really is going to matter is what's the surface area of that material. So two identical materials, one has 4 times the surface area of the other, could be a huge difference in toxicity. Of course, surface area scales with particle size. As the particles get smaller, you get more surface area. So these are 3 sort of independent toxicological mechanisms that could drive this issue of nanotoxicity. Here's a nice publication where they looked at these quantum nanodots. So we do a lot of, actually one of our researchers, actually the director of the lab now, director of Lawrence Berkeley Lab, he's actually the guy that hired me many years ago. And he does a lot of work with quantum nanodots. And they have some cool features. They fluoresce different colors depending upon their size. They can do things, you can get them inside of cells, and they'll attach to parts inside the cell, and they'll stay there through divisions, and you can track them through these whole life cycles, and actually visualize under a microscope what's going on, because these things actually fluoresce. There's a lot of potential use for that. This shows an example of the different fluorescence colors just based on the same chemistry, different particle size. Okay? So here was a study where they said, well, wait a minute. These cadmium-containing nanodots, they're going to be toxic by definition because they contain cadmium. But is that the whole story? So what they did was this was an in vitro study. And what they did was they measured the amount of, well, let's start this way. First they made a calibration curve. Okay, and this is metabolic activity. In other words, how many cells are still alive? 100% are alive up here. None are alive down here. On this axis is the concentration of cadmium ions, which is the toxic part of cadmium. Okay, they made a calibration curve. That means as the concentration of cadmium, just using cadmium salts, goes up, cell viability goes down until you get up here around 160 and all the cells are dead. Okay, just using soluble cadmium salts. Okay, so if the soluble salts were the sole part of the story, this is exactly what you would expect if you expose these cells now to quantum nanodots that contain cadmium. But what they actually found is that at much lower concentrations, these things were much more toxic. Okay? In other words, they were exhibiting toxicity that could not be ascribed to the dissolved cadmium ion. All right? So some sort of other toxicity, in addition to the cadmium ion toxicity. So you see, for example, these are different flavors of these lanthanum dots, cadmium telluride, cadmium selenide, so some different features. And some of these things are killing all the cells at much lower concentrations of dissolved cadmium because they're doing something else. And what it turns out, what else they do is the particle itself catalyzes various reactions inside your cell. And there's a bunch of these reactions. But the end point for all these things is they create what are called reactive oxygen species. These are things like, well, basically these are things that can oxidize. These are free radicals, these are peroxides, things like that. They can go around and chew up other molecules, okay, and do a lot of damage in your body. So-called, you know about antioxidants. What this does is induces oxidation. Okay, and that's a function of the particle itself that doesn't actually happen for larger particles. You only see that phenomenon where you get high surface area associated with small particles. Okay, So there's two forms of toxicity. Two of those mechanisms, elemental toxicity and surface area-driven toxicity, are happening at the same time for these quantum nanodots, which means they're much more toxic than would be expected just based on their cadmium concentration. Here's a nice graphic that I stole from some guy, although I give him credit down there, that shows if you take a small particle and start dividing it and dividing it and dividing it and dividing it, same mass, but you get this big increase in number of particles. So for example, down here you've cut it 8 times. You have 8 times the surface area. Okay, so you get this tremendous, for the same mass, you get this big increase in surface area. And if there's surface area-driven catalysis of reactive oxygen species, you get this new toxicity. Here's actually a graphic that's sort of a rough graphic, but it says, for a given nanoparticle diameter, this is the percentage of all the atoms in the molecule, called molecule, but nanoparticle. It really is the same thing. Okay? This is the percent of those that are on the surface of the nanoparticle. So by the time you're down below 5 nanometers on this axis, almost all the particles are on the surface. Remember the picture of the buckyball? Remember the picture of carbon nanotubes, single-wall carbon nanotubes? How many of those atoms are on the surface of that particle? All of them. Okay? Which means if those atoms can catalyze a reaction that's adverse, they're all there. Okay? So that's the idea of surface area-driven toxicity. And it turns out, it pans out for some things. The one area where this has been studied the most is with these particles that are, there's an acronym for it, I don't remember the acronym, but typically metals and metal oxides of low solubility and low elemental toxicity. Titanium, zirconium, barium, gold, polymers, fullerenes. These are things that are not, not intrinsically toxic. Really, titanium is pretty much a nerd. Zirconium. These things are not very intrinsically toxic. And if you compare the nanoparticle version of it to the microparticle version of it in terms of toxic effects in the lungs, you get 2 different curves. Well, yeah, I could do that. My microphone's still on me. So if you compare these 2 things, so this is think of this as toxicity. So this is a measure of toxicity. So the higher it goes, the more toxic it is. This is concentration, okay, or mass of exposure. So this is concentration, this is dose. That's a dose response curve. Okay, if you plot it for microscale particles, you get this curve. So by the time you get out here, they're 30 toxic on the toxicity scale. If you use the same chemistry but make the particles nanoscale, you see a vastly steeper curve. Okay, which means that the dose response curve is much steeper, and therefore, for a given dose, they're much more toxic. Same chemistry, different particle sizes. Things that are not very toxic to begin with all of a sudden start showing this increased level of toxicity. So, here you get to this level at 500 micrograms. Here with the microparticles, it's basically 4 times less toxic, just by virtue of the particle size. And it turns out, though, if you compare them not based on their size in terms of diameter, but compare them based on their calculated surface area, there's no difference. Okay, so this is the curve for the 2 sets of data, ultrafine and fine titanium dioxide, and they fall on the same curve, same toxicity curve, if instead of micrograms on this axis, you have surface area on this axis, which means that the nanoscale particles are more toxic only because they have more surface area that can be involved in this adverse catalytic reaction. Okay, so this is one of the big drivers of nanotoxicity. Does that make sense to everybody? Everybody understand? Okay. It's a little bit complicated topic. Let's take a look at carbon nanotubes a little bit, because I said these have been studied quite a bit. We looked at what carbon nanotubes were earlier. These long, thin tubes that can be micrometers in length, but are anywhere from 1 to 10 or 20 nanometers in diameter. Okay. So this is one of my soapbox things. So I've been following this one company. It got bought out by another company, and roughly once a year, I go and I download their MSDS for carbon nanotubes. And I've been doing this for like 8 years now. I did not do it this year, so this is from 2012. Okay, and the reason I do that is to this date, when on the MSDS they quote an occupational exposure limit for carbon nanotubes. They quote the OSHA standard for synthetic graphite, which is 15 milligrams per cubic meter total dust and 5 milligrams per cubic meter as respirable dust. And they also give the ACJH standard for graphite. Okay. Now, So is carbon nanotubes, are they just synthetic graphite? Is that all they are, toxicologically speaking? I don't think so. Okay, and we'll see where we're at on that. But nevertheless, as of last year anyway, this redacted name of a manufacturer is still putting out MSDSs that say this. So that's a lesson to all you guys right off the bat. Many MSDSs for nanomaterials are round file quality stuff. Okay? In fact, half the time, they won't even tell you it's nanoscale. And so you have to be very, very careful when applying anything from any MSDS, but certainly when as a nanomaterial. So they're recommending, or they're not recommending, they're saying the standard that you should apply is a synthetic graphite standard and 15 milligrams per cubic meter. That's basically a cloud, okay, like this kind of thing, like who are you, I can't see you, that sort of thing. That's what they're saying is, that's what they say the standard for carbon nanotubes is. I can't believe they haven't changed this in all the years. Now, they do have a couple of disclaimers later on saying, oh, you should look into it on your own. But they haven't changed this. So here's a couple of interesting micrographs, electron micrographs. This is a cross-section, we saw this earlier, through a multi-wall carbon nanotube. You see the walls. This is a side view that is drawn in here. 3.4 angstroms across. So that makes the whole thing, per one of these, so it makes the whole thing like 60, 70, 80 angstroms across and has this multi-layer structure. This is an electron microscope, the first that was ever published as far as I can tell, cross-section through a fiber of chrysotile asbestos. Okay, same diameter, same lamellar structure. Okay, so you really have to ask yourself, is there going to be similar toxicity to this? Because they basically look the same. Okay, they're both very skinny, very long, and in the case of chrysotile, has this multi-layer structure. Now, this idea of fiber toxicity is a study into itself. It turns out, and this hypothesis has been out there for 30 years now, and has been moderately robust as a hypothesis, that if you have any fibrous material that meets certain criteria with respect to shape, size, and durability once it's inhaled into your lungs, then you're at risk of developing chronic illness from that fiber. Okay, and so there's a place in Turkey that I really want to visit, but I can't find anybody who wants to go there with me, where they have these weird hoodoos, rock hoodoos. And historically, people have mined into those to build houses. In fact, they still have a hotel. They've got a hotel mined out of these rock hoodoos over there. Turns out these rock hoodoos contain fibrous minerals, arenite and zeolite. Okay, and so, especially among the old people that were really involved back in the day when they were really drilling into the rocks, massive levels of mesothelioma among these people. Okay, so this is not asbestos, because asbestos is just a term of commerce anyway. But these are materials that meet the size, shape, nano size, long skinny shape, and biodurability requirements to become toxic inside your lungs. Okay, and there's many examples like this. If you meet those criteria, you are at high risk. You really need to look at the possible chronic effects. So then you ask yourself, well, carbon nanotubes, how long do they last when they get in your lungs? That was answered originally by a woman from Belgium, Julie Mueller, and she said 50 to 60 to 70 days. It turns out that's right around the cusp between not going to cause cancer and going to cause cancer, right about in the middle. So if it had been way on one side, you'd say, oh, or way on the other side. But it's right there in the gray area, down the middle. So one of the issues you get into is these long, skinny things cannot be effectively removed from your lungs. And they kill the macrophages in your lungs that try to engulf them. And this triggers a series of events that leads to scarring of the lungs and cancer. Here's a very classic picture of a macrophage choking on chrysotile asbestos. Here's a more recent picture of a macrophage choking on a carbon nanotube bundle. And you can see there's no way those cells can actually engulf those materials. In fact, they start leaking contents of the cells. The macrophages are designed to destroy, so you're releasing materials that are designed to destroy. You get this problem. So there's all these things lined up to say that carbon nanotubes might be really bad. So how does that work out? Well, let me define a couple of terms first. One thing we're going to see is carbon nanotubes cause granulomas. So granulomas are these foreign body reactions that basically your body builds barriers and walls and fiber and to close off some particle that's causing some irritation. Here's some really gory examples I got from the internet of external granulomas. Imagine much smaller than that, but inside your lungs. And we'll see that's one of the things that carbon nanotubes causes. Pulmonary fibrosis, in case you don't know, it's basically just a scarring of the lungs. Asbestos causes that, quartz causes that, a lot of things cause that. In the case of asbestos, it's called asbestosis. And we'll see that the carbon nanotubes, at least in animals, do exactly the same thing, cause scarring of the lungs. Mesothelioma. Mesothelioma is a cancer of the lining of your digestive tract and your lungs. And fairly uniquely, in the United States anyway, it's caused by asbestos exposure. Okay, so most people that develop meso have some significant history of occupational asbestos exposure. Now, in Turkey, in that Anatolia region of Turkey, people have very high rates of mesothelioma because of where they lived and the kind of work that they did in just the rock that's there. And we'll see, so we're going to talk about these kinds of terms in context of carbon nanotubes. Lung cancer, well, I think everybody knows what lung cancer is. So, I like it. 100 years old. So here's that first study. I mentioned this briefly earlier on. This was 2004 by a guy from the CIIT. Okay, and he put out a study saying, don't worry about these carbon nanotubes. Yeah, we killed a bunch of rats, but it's because we choked them to death. Okay, but other than that, I wouldn't worry about it. We didn't see any problems. So I said, what is CIIT? I didn't know what that was. So I went to the website. I searched for 10 minutes before I found out it was the Chemical Institute of Industrial Toxicology. Okay, so this is from the manufacturer of these kind of materials. So it turns out his study, not only that, but he was using incredibly impure carbon nanotubes that had up to 50% of the residual catalyst that was used to make them. And the residual catalyst is often in and of itself toxic. So this guy was pretty much the first to market with this study. Pretty much round file, okay? Then there were better studies that came out. And these were all installation studies, or what is called, what's the other term for it? Inspiration studies, where they make the rat or mouse choke on the carbon nanotube solution, and they gasp and they suck it into their lungs. So these are not inhalation studies. But nobody did inhalation studies for a long time. So Lamb from NASA was using a lot of carbon nanotubes. They said, what's going on? Lamb concluded that if nanotubes reach the lung, they're much more toxic than carbon black and can be much more toxic than quartz. Of course, quartz is very toxic. Shevdova from NIOSH, she's still working there. As far as I know, she's still there. If workers are exposed to respirable single-wall carbon nanotubes at the current PEL for graphite, remember we talked about the graphite PEL, they may be at risk of developing some lung lesions. Julie Mueller came up with this beautiful article in 2005. If multi-wall carbon nanotubes reach the lung, they're biopersistent. She was the first person to determine that, and induced lung inflammation and fibrosis. Heshko from 2005. He had earlier published an article saying, don't worry about it. He redid his research and said, forget that. And this stuff is actually very dangerous. So we had early on a pretty strong indication that this stuff was going to be toxic. Of course, we want to really know what happens when you inhale these. Now, we had that first study from Loveless. That's the name of the place in Albuquerque, where they used the non-carbon nanotube carbon nanotubes in the study, and so that isn't too useful and suggests the authors are not very credible. This was the first useful inhalation study that got published by NIOSH, and this was 2008. God, it's been that long. See Anna Shevdova there at the beginning, and Vince Castronova, Paul Barron, he's died since then, Kagan. And their conclusion was, when you allow the animals to inhale the carbon nanotubes rather than having them instilled, much worse. Okay, 2 to 4 times the lung inflation, 2 to 4 times the diffuse fibrosis, gene mutations. Based on the outcome of our inhalation study, it will be inferred that if workers are subject to long-term exposure to respirable single-wall carbon nanotubes at the current PEL for synthetic graphite, they'd be likely to have increased risk for pulmonary changes, which I'm sure is very politically carefully stated. Okay. And so the bottom line is this was the first study. Now then, in 2008, the EPA said, well, wait a minute. People are putting these things in commerce, and I don't see them on the TSCA list of registered chemicals. Carbon nanotubes are not on that list. So they started requiring people that would put these things into commerce to do toxicology studies, only 90-day subchronic exposure studies. But they required it, and the industry then started publishing some results. Okay, this is from BASF, which, by the way, has done a lot of really good work in this field. I mean, I have a lot of respect for the work they've done. This is a mouse or whatever they were using. That's their long-after carbon nanotube exposure. And what they determined that, let's see, what did they actually say? Increased lung weight, pronounced multifocal granulomatous inflammation, diffuse histolytic and neutrophilic inflammation, intraalveolar lipoproteinosis, scarring. And they were dose dependent, but the lowest dose they used was 0.1 milligram per cubic meter, and they still found toxicity at that level. So they were not able to establish a no observed effect level because they didn't go low enough. Now that's at 0.1, that's at 0.1, so 0.1 milligram per cubic meter. Remember the standard that they had on an MSDS, depending upon the cut fraction, 15 or 5 milligrams per cubic meter. So even taking the 5, okay, which is the respirable range, this shows that at 50 times lower than that, they're still seeing this toxic effect in a lousy 90-day study. Okay, now Bayer published some stuff, and Bayer's done some good work in this regard too. And let's see, they basically concluded, it's a little hard for you guys to read, but it said they found a no effect level, and they identified their no effect level at 0.1 milligram per cubic meter. Anything above that caused clear toxicity. And they recommended an occupational exposure limit of half of that, 0.05 milligrams per cubic meter. Now, there's also an asterisk on this, and I don't know where that asterisk is, but somewhere. The particles they make are specifically designed to be short and highly tangled. In other words, to not fit the hypothesis for fiber-induced lung toxicity very well. And so they tell you that, yeah, this is what we saw. It may have nothing to do with your carbon nanotubes. Okay, because ours are designed to be short and tangled, which is the opposite of what you'd expect in terms of inducing toxicity. So they're recommending 0.05. Okay, so that's 100 times less than the standard, than the graphite standard. So all these people are finding this inflammation, these granulomas, this fibrosis, this scarring, all this bad stuff like that. But what about the question of cancer? Well, a couple of articles came out in 2008. Okay, and these were very controversial. What they did, and apparently this is pretty common in Europe, is that they injected carbon nanotubes intraperitoneally, in other words, into the gut of rats or mice. I guess it was mice. Okay, and in the latter study, they used mice that are predisposed to develop mesothelioma anyway. Okay, and they said, well, you know, the mesothelium is going to be exposed to these particles just like they would if you inhale them and they migrate out of your lungs. So what might happen here? So they had a couple of interesting results. Now, just this method of study is controversial, and not everybody thinks it's valid, but it's actually, in parts of the world, pretty standard. So let me walk you through this slide a little bit. This is from the first study. This is from the Poland study. And what they were looking at is inflammatory response at 1 day post-exposure and granuloma, which is another kind of inflammation response, 7-day post-exposure. And what they were comparing here was the vehicle, the liquid that this was injected into the lungs, the vehicle itself. This is a graph of toxicity, okay? And you see the vehicle caused very low toxicity. This is carbon black. So they're like carbon nanotubes, except they're not long and skinny. Almost no toxicity. Short fiber amosite asbestos, very low toxicity. Short fiber nanotubes, yeah, a little bit more, but not statistically significant difference. Okay. Now they said, what about long fiber amosite and long fiber carbon nanotubes? You see this huge jump in inflammatory response, both in right off the bat and a week down later, even though they're slightly different measures. You see this huge jump in inflammation as soon as you go to the long, skinny fibers. So this strongly supports the notion that the shape has everything to do with this. Or at least not everything maybe, but has a heck of a lot to do with this. Now this study, this is perhaps the most controversial study. This involved mice that are predisposed to develop meso anyway. And what they compared was crucidolite asbestos, which is the most potent mesothelioma gen, in other words, something that causes meso, that we know about. And they compared it to long multi-wall carbon nanotubes. And this is simply cumulative death due to mesothelioma, 100% at the top, and days after exposure on the bottom. So it's a simple dose-response curve. How many animals die from meso over a given time? This curve out here, which only goes this high and takes this long, that's for the crucidolite asbestos. This much steeper and earlier and essentially almost 100% curve is for the long carbon nanotubes. Okay, now, having shown that, and it's very dramatic and all that, be aware that there is a huge controversy surrounding this, and some people think it's relevant, some people think it's not relevant, but the truth is, what you really want is a lifetime animal inhalation study where they look for these endpoints. Hasn't been published yet. So we have to go with what we have, and right now, long fiber multi-wall carbon nanotubes look at least as toxic as asbestos in terms of inducing mesothelioma as a form of cancer. So pretty nasty stuff. So is this 15 milligrams per cubic meter and 5 milligrams per cubic meter valid? Well, we've seen it really isn't. Some countries have started proposing standards now. So Bayer, we saw Bayer earlier, they proposed a standard of 0.05 for their carbon nanotubes, okay, which is a specific brand of carbon nanotubes, Baytube. Okay, Japan has now proposed a standard of 0.03 milligrams per cubic meter. EU is kicking around a standard of 0.05, which I think is based basically on the Bayer stuff. NIOSH has put forth a recommended exposure limit. And NIOSH has put that forth at 0.007 milligrams per cubic meter. They established that as the exposure limit because that's as low as you can monitor with routine industrial hygiene practices. They say that there's actually still a pretty high, based on the tox studies, pretty high residual risk of lung damage even at that exposure level. And if you look at their research, really their no effect level is about an order of magnitude lower than that. But the truth is the method that they propose for doing this is not easily adapted to have that level of sensitivity. So they essentially set it at the limit of detection, okay, for the readily available methodology that's cheap and easy for people to do. It doesn't cost $1,000 a sample like some of these samples cost. So all of these are a heck of a lot lower than 15 or 5. And this is the realm that really are probably most appropriate for carbon nanotubes, down in this sort of scale. Now at LBL, because we can, that's the main reason, because we can, our criteria is no detectable exposure to any engineered nanomaterials. Okay? Question?
Could you put it in perspective? Like, is this what's proposed to be used in drugs and other products, or is this something that we're already exposed to in like exhaust vehicles?
Well,
what are we talking about as far as like current exposure and
yeah.
potential?
So we talked about a lot of the products that want to put it in car tires. That hasn't happened yet, but a lot of graphite. A lot of composite materials that are being manufactured, so tennis rackets, bicycles, baseball bats, all those kinds of things like that. So there are literally hundreds now of applications of carbon nanotubes being used in industry. The one company I went over and did a presentation for, that turns out it's very useful in electromagnetic pulse shielding in military electronics. And so I don't know exactly how they're using it, and I don't want to know, but they're using it as a barrier to EMP effects. Because if you make these carbon nanotubes right, they're unbelievably electrically conductive. So I imagine they're shrouding their electronics in these kind of blankets and things like that, although I don't know exactly what they're doing. And so there's more and more. They're still kind of expensive, so they're still mostly in high-end kind of applications. But as I said, they want to put them in car tires. And car tires wear away, and that's going to be released into the environment. Now, there is some background level of carbon nanotubes from forest fires and stuff like that, but it's very low. If you sample the air long enough, you will find some carbon nanotubes in it. Question?
So we go out and inspect facilities that are trying to develop nanotube technologies and growing nanotubes and stuff like that. What is the risk at a facility like that?
So NIOSH has published some data. And other people have published some data on carbon nanotubes. And they find pretty significant potential for exposure in these little factories. Way above this. I don't have I don't have a slide for the NIOSH data, but they find factors with exposures well above this. Okay, there is a saving grace in that these carbon nanotubes stick to each other very aggressively, and so they're not that easily aerosolized. But you can imagine in a factory setting, you slice open the bag, pour it into the hopper, it grinds it, then it spews it down some sort of hopper, it goes into a thing, you open it up. So in those kind of settings, they are seeing some significant exposure, not just to carbon nanotubes, but other nanomaterials. So NIOSH has a pretty aggressive program to go out into industry and look for these things. And they have, I've been to many presentations by NIOSH, and they have all sorts of graphics, electron micrographs showing particles they got out of the air. Some people are getting some pretty good exposures. And as we'll see, the EPA has actually intervened on carbon nanotubes, and they're establishing occupational protection standards because OSHA is never going to do it. So the bottom line is there potential for exposure in the current industry that's happening out there? Absolutely. Question?
What do you guys use for protection?
Well, like I said, we allow zero exposure because we can. And the reason we can is that our scale is so incredibly small that just using standard laboratory practices eliminates exposure. So for example, a guy that's making carbon nanotubes is probably making 300 or 400 micrograms. if that. So scale like this. Oh, you got a bunch of nanoparticles? Yeah, and he picks up a little vial, that big, and that's his nanoparticles. That's pretty much the scale we operate on at LBL, and at least so far. And as a result of that, it's not hard to control using standard laboratory practices. Okay, and it turns out it's highly dependent. As I said, carbon nanotubes tend to stick together pretty aggressively, so you have to do some work to get them to fly apart. But we also make a lot of these nanowires. And so I monitored one operation, indium gallium nitride nanowire. They grow it on a surface, and you get this forest of these vertical nanowires. And then they wanted to transfer some of those to what's called a TEM grid. Basically, just scrape it with this piece of copper. They put the copper in the electron microscope. When they did that, there were fibers all over the place. Boom, just like that. So it's very highly dependent upon the exact product you're working with. And the problem is, and I won't talk a lot about this because this gets too industrial hygiene-y, if you use simple techniques to measure particles, right now in this room, there's probably between 2,000 and 5,000 nanoparticles per cc, because the cars are making nanoparticles, the ocean is making nanoparticles, thunderstorms are making nanoparticles, volcanoes are making nanoparticles, China's making nanoparticles. So if I were to monitor in here right now with a direct reading instrument, I'd see at least 1,500, 2,000 nanoparticles per cubic centimeter of air. So now you want to measure an engineered nanoparticle. You've got that huge background to deal with. And you've got to find a way to overcome that huge background. And there's different ways to do that. We've actually pioneered a method at LBL. I had a grad student, and she and I pioneered this method, where people would say, look, I don't want to work in a fume hood because my particles are so fine. There's too much wind in a fume hood. I want to work at a benchtop. We have a glove box with no bottom. So we'd say, okay, set up your experiment on a benchtop. So we give them a tray, like a cafeteria tray, and they'd set up what they want to do with their nanoparticles and all that. Then we would drop this glove box over it, and we'd use a HEPA filter to completely get rid of all the particles inside the glove box. So we'd have zero background in the glove box. Now we tell the scientists, okay, use the gloves and do whatever it is you're going to do, whatever you're going to do to your nanoparticles. And meanwhile, we're measuring with a direct reading instrument. And instead of working against a background of 2,000, working against a background of 0. And so we can see stuff that nobody else can see. And so that's the criteria we apply to our research labs. Is with the technology that's better than anybody else's, we don't want to see anything. And that's because we can't. In a factory, that's not realistic. Okay? But in our setting, we haven't encountered an operation where it's not realistic yet. Question?
Would current respirators be able to filter out nanoparticles?
We'll talk about that. The answer is yes, but we'll talk about that in just a minute. Question?
From a hazardous waste perspective, how can we manage the end of life of these products when they're going to break down and end up in the landfill or get incinerated?
Well, we'll talk about that a little bit later on, too. So the question of hazardous waste. So now you've got a pile of nanoparticles. What is the regulation in terms of hazardous waste? And the answer is there really is nothing specific for nano, okay? Which means if your particle is otherwise regulated as hazardous waste because it's ignitable or reactive or contains cadmium or something like that, then it's a hazardous waste. If it doesn't meet any of those criteria, like, well, certainly titanium dioxide doesn't meet any of those criteria, zinc oxide doesn't meet any of those, well, maybe zinc. Titanium oxide doesn't meet any of those criteria. There's nothing that says it has to be treated as hazardous waste. Now,
Carcinogen as a nanoparticle, though, titanium dioxide.
maybe.
IARC.
Maybe. Yeah, but those are not regulated as hazardous waste. So now the University of California, we were sort of the first, the DOE was the first, but now that's spread to the whole, the university and the state DTSC published a guidance document about 10 months ago. And their recommendation is if it's nano, handle it as hazardous waste. And we've been doing that for 7 years. So anybody that generates any nano, even if it would not otherwise be regulated as hazardous waste, it gets marked as toxic. It gets the waste label stuck on there. It gets put into the SAA. It gets transferred to the WAA. And it gets out and gets buried or burned or whatever it is they do with it on the other end. So we do that whether it's... Now, a lot of it is hazardous, if not because of the particle, because of the flammable solvent that it's in. But a lot of it would not otherwise be classified. But at the university, and certainly at the DOE lab complexes, we long ago decided we don't want to put that in landfill and worry about that 20 years down the line. So we treat it all as hazardous waste. Now, I don't know some of the details. For example, I guess you can't just wave your arm and declare something hazardous waste. It's actually not legal. But you can treat it as hazardous waste. And at the very end, there's probably some paper you sign, oh, it's not really hazardous, but burn it anyway. I don't exactly know how that works, but maybe Steve can comment on that. I don't know. But in any case, we treat it as hazardous waste, all of it. Contaminated gloves, contaminated coveralls, contaminated respirator filters, all of it hazardous waste, without any further thought. Okay. There's other things that you have to worry about. It turns out that nanoparticles that land in your nose can, to some extent, be transported up the axons into your brain from that location. Intact nanoparticles. Okay. And at least in rats, in studies they've done in rats, they've showed you can expose them to metal nanoparticles by the nose. The particles themselves end up in the brain where they cause brain inflammation. Now, those are rats. And whether or not that translates 100% to humans isn't all that clear at this point. Rats have unusual brains and unusual noses. But the bottom line is there's a suggestion that there's these route of exposure that don't occur for macroscale particles. Macroscale particles that land in your nose either dissolve or you spit them out, or you swallow them and then they get removed from your body that way. Nanoscale particles can go intact into your nerves. It turns out this happens in your bronchial tree too. Here's pictures of some very small fluorescent rhodamine beads being transported in a neuron cell body away from the lungs. So nanoparticles that land in your lungs, among the other things they can do is they can end up being transported into the ganglia and along axons with, frankly, unknown health effects. Okay. Plus, this other phenomenon that's very clear now, and this is kind of predictable, actually, but it turns out it wasn't clear until relatively recently, is that if you inhale nanoparticles and they land in your lungs, they cause systemic toxicity unrelated to any moving out of the lungs. So in this case, titanium dioxide. These animals were exposed to titanium dioxide. That's the control animal. This is the experimental animal that got the titanium dioxide exposure into their lungs. Okay? And these are indications of oxidative stress and basically vascular malfunction and vascular oxidation that happen just because of some cascade of events that initiates when these things land in your lungs. It used to be thought that maybe this was caused by particles that leave your lungs, get into the bloodstream, land in the arteries, and cause this effect. That ain't the case. This causes some sort of a biochemical cascade that actually reduces the compliance, reduces the responsiveness of your vascular, and causes this sort of inflammation. And in fact, in this study, this involved rats that were predisposed to develop atherosclerosis. These are the controls on top. The dark red, or the bright red, indicates atherosclerosis. See a lot more of it on the bottom in the single-wall carbon nanotube exposed animals. Okay, so you get this inflammation. Inflammation is related to atherosclerosis. So you're getting systemic toxicity from lung exposure without translocation out of the lung. Now, one of the newest things on the scene, good for a Nobel Prize a couple of years ago, is graphene. Graphene is just a single layer of graphite. So why that's new, I don't know, but it is. And so if you imagine, so graphite, when you write with a pencil, layers of graphene are coming off. Thick layers, but they're coming off, and you make a mark on the page. If you can separate it down to get a single layer, or just a couple layers, you've got this graphene material, single layer of carbon, that then apparently has some miraculous properties. It was good enough for a Nobel Prize, possible use in composites, polymers, electrodes, supercapacitors, all sorts of different things. Okay. Now, there's only been a couple studies published, but it indicates that those might be pretty toxic too. Now, they're kind of interesting because they're not necessarily nanoscale in length or width. They're only nanoscale in depth. Okay. And I would imagine it's going to take a lot of studies. These are the two that I've seen. This latter one, aspiration and installation of micron-scale graphene, but very thin, nanoscale thickness, caused significant lung inflammation with evidence of frustrated phagocytosis. In other words, making it so the macrophages can't survive. Okay, so graphene may be the next thing on the market too that we have to worry about. Let's talk a little bit about regulations, because you guys have a lot to do with regulations. Let's talk a little bit about that. It's not my area of expertise, but I know enough about it to give you guys a start on this. Actually, Berkeley was about the first municipality to try to regulate nanoparticles. Okay, and actually this happened in December 2006. I started there in the summer of 2005, so I got a chance to consult with the city and make recommendations, all of which, of course, they completely ignored. And this is now an add-on to the HMBP process. You have to disclose your nanoparticles, and there's a bunch of things you have to do for the city. Now, my advice to them was, it's both unnecessary and very difficult to deal with this in an R&D setting where we make different nanoparticles every day of the week in scales that are that big. And I told them that, like everybody else, they should exempt scales that are that big from the regulation, which they did not do. As a result, the university and the lab only partially comply. We comply with the spirit, if not the letter, of the law, because we're not subject to regulation by Berkeley in this arena. Okay, we have to submit hazardous materials business plans, but this part of it is City of Berkeley only, so we're not actually subject to that. Although we do comply with the bulk of it. We just don't give all the nuances of today he's doing that, tomorrow he's doing that, the next day he's doing that, which the city otherwise seems to want. And they seem happy enough with that. So this was the first nano ordinance, which has been criticized because there's no de minimis quantities. The reporting format is pretty vague. Actually, I get asked. Coming through the Molecular Foundry, we have a lot of people that if they can develop something while they're researching in the Molecular Foundry, they're going to get $7 million of venture capital, and they're going to go out and start a pilot factory. And I've been asked several times, well, where do you think we should start our factory? And I basically say, not in Berkeley. And they say, oh, well, we already figured that. So Cambridge, Massachusetts considered something like this, but they never followed through on it. So that's the only place that has that sort of local ordinance. Now, the state of California, DTSC, has done some work. And they have actually done some pretty good work. I give them a lot of credit. They have this ability to do call-ins, basically demand from people information on materials they're working with, including nanoparticles. And they've had a couple of call-ins for nanoparticles, carbon nanotubes, and then an assortment of metal and metal oxide nanoparticles, quantum nanodots, and things like that. They've had a couple of these. They had a bunch of meetings, many of which I went to, some of which were productive. So they gathered this fairly big data set with the idea being that they wanted to know what they were missing. Some of the people that submitted data, all the data that people submitted got published online. Some of it was very good. So some people did a good job. Other people didn't respond at all. I don't know how they compel them to respond. I think they can. I don't know how they do it, though. So they've got this database that they're working on. But their current activities in terms of moving towards regulation have been pretty limited. They are working on nanosilver, because nanosilver is mostly used as a pesticide. Okay, so they have a whole other line of potential authority to regulate there. So they actually have some activities going on nanosilver, though they're a long way from regulation. It's going to be years before we see anything in the way of regulation. Then the other thing they worked on, they worked collaboratively with a bunch of universities, including a bunch of the UC campuses, to come up with a safety and health guideline for nanotechnology research, which they published about 10 months ago, which is very good. It's a very nice document, really not very much different from what we've been doing since 2005. A little bit different. It's a nice document. So if you work in that sort of setting, it's a good reference tool for looking at how to protect people in a research setting. It's not really very applicable to a factory setting like a lot of you guys might visit. So that's pretty much all that's happening as far as I can tell at the DTSC level in the state of California. OSHA, well, OSHA hasn't, neither federal nor state OSHA has done anything with respect to nanoparticles. Now they'll tell you immediately, oh, well, the respirator requirement applies, the PPE standard applies, all these standards still apply like anything else, but nothing specific for nanoparticles. And I know some OSHA people that are involved in standard setting, and there's nothing that you could expect in the rest of my career anyway. So there's nothing there. EPA. Now, EPA has a number of different authorities by which they can potentially regulate nanoparticles. They can regulate them under TSCA, which they've been doing for carbon nanotubes. We'll talk about that later on. They can regulate them as a pesticide under FIFRA, which they are working on for nanosilver. I looked up the due date when they figure they'll be done studying it, 2017. So they might be ready for some regulatory action in 2017. So there's nothing you would expect to happen in terms of regulation before then. They can prohibit releases to air, Clean Air Act, or water, Clean Water Act, Safe Drinking Water Act. They can classify it as a hazardous waste under RCRA. I don't really know of any activity in those categories. There might be something, but whatever it is, it's pretty low key. The main one has been TSCA and FIFRA. So let's talk about TSCA a little bit, Toxic Substance Control Act. So you can only market chemical compounds that are on the inventory of the EPA Toxic Substance Control Act. So there's something like 86,000 or 90,000 or whatever it is, materials on that inventory. And they said, wait a minute, what about nano? The EPA decided that if you have nanoscale titanium dioxide or nanoscale zinc or nanoscale most things, that they are fundamentally no different from microscale of the exact same chemical and therefore not subject to selective regulation under TSCA. So if you're making most nano things that are just littler versions of the bigger stuff, no TSCA requirements, okay, for the most part. There are exceptions to that. But they say carbon nanotubes. I don't think those are fundamentally new. So they started regulating carbon nanotubes, all right, because they could. And so in 2008, they published this announcement of regulation on import and manufacturing. And this basically requires now people that want to manufacture and distribute these materials to do a bunch of different things. Basically, step number one is they have to submit a notice to the EPA that says, yeah, we're going to start making this stuff and we're going to start selling this stuff. Then the EPA will enter into a consent decree with them. And so these PMNs, pre-manufacturer notices, are what they submit now to the EPA. And the EPA will look at their data and they'll enter into this consent decree with that particular company. Okay, so-called 5E consent decree. And for the carbon nanotube stuff, they did a couple things. One is, you're only approved to use it for whatever you wrote down in your application. So if you're approved to use it for polymer composite materials, electronics, catalyst support, which is some of the early applications, that's what it said, that's all they're approving. And as we'll see, if you want to do anything else with it, you're back to the beginning. Okay? You're required to conduct a 90-day rat inhalation toxicity study, hence BASF, hence all these corporations that are now doing toxicity studies because they have to. Because you can't market them in the United States without doing that. Part of the problem is EPA has recognized there is no one thing such as carbon nanotubes. There's hundreds probably of variations on the theme. We've already seen short tangled are much less toxic than long skinny, and then you've got multi-wall, 5-wall, 6-wall, 10-wall. You got a whole different lot of variation in the theme. So they're pretty much approving these things on a manufacturer by manufacturer basis. Here's the cool part. Since OSHA's not doing anything, part of the consent decree is they require employers who may be exposed to use specified types of personal protective equipment, including full-face respirators, protective coveralls, and gloves. That's something that should come out of OSHA, right? That's not going to happen, but that came out as part of the consent decree for carbon nanotubes. I like the one at the bottom in red, only allowed to distribute the materials to persons who agree to comply with all the restrictions. In other words, you can't sell it to anybody who's going to use it for something else. You can't sell it to anybody who's not going to use a full-face respirator, protective coveralls, and gloves where there's potential for exposure. You're not permitted to sell it to those people. So, actually, just trying to go online to get some of the MSDSs from some of these more sophisticated companies. You go online and say, I want your carbon nanotube MSDS. You get a call. What do you want? And I say, why are you interested in our carbon nanotubes? What kind of research, what kind of work do you do? Who are you? Do you have any background? You get grilled because they're subject to this consent decree limitations on who they sell this stuff to. I mean, some of it's pretty funny, actually. Oh, yeah, I heard about toxicity. I heard about that. Now, after issuing these consent decrees that only apply to that manufacturer, they then issue what's called a SNUR, Significant New Use Rules. And that means that anybody that's going to use those carbon nanotubes from that particular manufacturer have to follow the same rules. Okay, so this applies then to everybody. And the interesting thing is, let's say you start making carbon nanotubes. They may or may not be different from that one that's already been approved. So you have to then submit to the EPA and ask them, actually it's sort of an informal process, are these the same? Can I work under this SNUR? Or do I have to go through the process again on my own? They'll make a determination. Sometimes they've required a new SNUR or new consent decree. Sometimes they've said, yeah, it falls under that same category. Kind of depends. They look at, I don't know what they look at, but they look at something. So they said, but if you're going to use this stuff and you're going to have any new uses, then you've got to go through a big review. And what are new uses? Well, one of them, A, using it for something that wasn't listed on the original application. And B, significant new uses are deemed to occur when an employee does not use gloves, impervious nanoscale particles, chemical protective clothing, and a NIOSH full-face respirator with N100 cartridges. So if you're going to go to work with this and not use those protective devices, you've got to submit to the EPA for permission to do that. Because that's significant new use that has not been previously permitted. So this is interesting. And now that's pretty much I'll say there's an exemption for research. So at LBL, we fall under this exemption because we use small quantities for R&D, standard lab procedures, only handled by technically qualified people. So we fall under the exemption, which is perfectly reasonable for the kind of scale work we do. And that's pretty much where the EPA is at on these things. Remember, they can't regulate under TSCA most of these things because they're not new enough to be called new. But for carbon nanotubes and a certain number of other nanoparticles, they can regulate them under TSCA. And they are pursuing this regulation of nanosilver under FIFRA. But again, I read their timeline. They'll be done in 2017, so maybe then something will happen. By then, I'll be retired and on the beach. Of course, the lawyers are out there looking to see if they can make a buck. Honest to God, this happened. I got subpoenaed for some work I did when I worked for UC Berkeley back in '87. And it was for one line on a training outline I put together. They wanted to grill me for hours based on one line I had put in an asbestos training outline. I hired a new tech, and this was an outline for training the new tech. That doesn't matter too much, but the part that was interesting is our lawyer, the one the university hired to defend us, he had gone online, figured out who I was, and downloaded one of my presentations that were online on carbon nanotube toxicity. And he said, well, I got 3 kids to put through college. Is this going to be big for the future? Am I going to be able to make some money on this? That's our guy. I said, that's the kind of lawyer you want. A real shyster. Okay. Here he was thinking of putting his kids through college on carbon nanotubes. And I think basically he beat the argument that this poor guy with mesothelioma was making was unimaginably weak argument. And I couldn't imagine that even in the United States that could hold any water, and I guess it didn't. Anyway, so somebody asked about safety controls. Believe it or not, when I went to my first nanotechnology and health conference back in '05, there were all these questions. Will respirator filters work? Will HEPA filters work? What about gloves? What about all these things? Are they actually going to work? There was this model out there that this guy had published saying that filters, HEPA filters, were not going to work for nanoscale particles. Even pretty big nanoscale particles, like 10 nanometers. They just weren't going to work based on theory. Okay. Now, since that time, that's all been debunked. So I'll tell you why Since that time, that's all been debunked. And so the easy answer is pretty much respirators work pretty much like you'd expect. There are some nuances we'll look at briefly, but pretty much they work fine. Impermeable gloves pretty much work fine. Coveralls, they never work well. I mean, that's just by definition, so you can't really expect coveralls to keep things off of people completely, but they help. But the whole thing about filters and HEPA filters and blowers and HEPA filters on roof, that's all been resolved. This is a filtration curve for pretty much any mechanical filter. Let's just imagine for a minute that it's a HEPA filter, even though it's not. Okay? This shows the effectiveness. So up here means it's very effective. As this curve drops down, it means it becomes less effective. Okay? And this is graphed on the particle diameter. This is 1 micrometer. This is a tenth of a micrometer, 100 nanometers. That's a hundredth of a micrometer, 10 nanometers. And for a typical filter, what you see is at the larger particle sizes, very high efficiency. And then that tails off into you're in this range of about 0.1, 0.2, 0.3 nanometers in size. That's the low point in filtration efficiency. Okay, that's why if you know anything about HEPA filters, they're tested at what particle size? 0.03 micrometers. That's because that's right here. That's the worst point on the filtration curve. As the particles get smaller, the efficiency becomes better. Okay, now notice this curve stops at around 20 or 30 nanometers, so this curve doesn't go any further down that. So there have been some studies. One thing I'll tell you, for a mechanical filter like a HEPA filter, forget about it, it works fine. If you can get down to nanoparticles on the order of 1.5 to 2 nanometers in size, then it starts to fall apart. But the truth is, in the real world, getting independent nanoparticles 2 nanometers in size is damn near impossible. Okay, so in the real world, HEPA filters work exactly like you'd expect them to, very high efficiency. Even like in the building I work in, the crappy housekeeping filters in the ventilation system cut down the nanoparticle concentration by a factor of 3. Okay, because it turns out nanoparticles are easy to collect by filters, much more easy than these 300 nanometer size particles that are hard to collect by filters. Now it turns out respirators are a little bit different, especially not in the case of HEPA filter respirators, but in the case of filtering face pieces and things like that. They're mostly not so-called mechanical filters, they're electrostatic filters. They depend upon electrostatic attraction within the filter to hold the dust. There it turns out, this is data from NIOSH, rather than the most penetrating particle size being 300 nanometers, There, the most penetrating particle size is around 30 or 40 nanometers. So this means is there is a shift to smaller particles in terms of their ability to penetrate these filters. So if you're wearing a disposable dust mask, it's almost certainly an electric filter. That means the smaller particles are going to preferentially get through. But even considering that, the efficiency at worst was 98%, which is more than you can count on anyway for that kind of respirator. So it works to the level that you should be counting on it to work. If you count on it for more than 95%, you're doing it wrong. Okay, so it turns out all these things, gloves, respirators, there was even this thought that ventilation systems wouldn't work. I'm thinking to myself, I've been an industrial hygienist for all these years. How can ventilation not work when it works for welding fume? What are you guys talking about? Are you crazy? Hey, we had a big scientist come to and say ventilation wouldn't work. So I don't know what you're talking about. Turns out ventilation works exactly as you'd expect it to. Okay, so if you want to, this is some NIOSH pictures where they went out in the field and they installed this local exhaust ventilation system, and it greatly reduced concentration. Some data from UMass Lowell where they looked at the effectiveness of fume hood, incredibly effective. Fume hoods, when they're properly operated, are very effective. So there's nothing weird about capturing nanoparticles in ventilation, on filters, any of that stuff. It's all pretty much ordinary. And again, personally, I didn't think there was any reason to think it would be other than that, but there was a lot of confusion at first. Okay, so that's pretty much the presentation. I'll show you a bunch of guidance documents up here. Some of these, there might be slightly newer versions of these things. These are the kind of things you can go on the web. Some of them you can download, some of them you have to pay for. And these are useful documents. I said in April 2000, I don't have a picture of it, but in April 2012, GTSC and the universities put out a guidance document for R&D. That's the best document for R&D. NIOSH approaches to safe nanotechnology. ASTM, Standard Guide for Handling Unbound Engineered Nanoscale Particulates in Occupational Settings. Current Intelligence Bulletin from NIOSH. There might be, this is their medical screening document. I think the final one of these has come out now, where they don't actually say all that much. ISO Technical Report from 2008. A whole bunch of different guidance documents out there. So when I started this business in 2005, there were no guidance documents. And I worked in a group that developed the first one ever. Okay? But now there's many. So we stopped making our own because it's not needed anymore. But for several years we maintained that, and that was sort of the standard document that everybody referred to. Turned out to be a problem. It was a guidance document, which means it's just good practice. But the DOE decided, well, it's all there is, so we're going to make it mandatory. We said, well, we wouldn't have written it that way if it was mandatory. That's always the risk you take working for the government. Here's actually a picture. Those are carbon nanotubes being poured back and forth between buckets with an air monitoring filter up here. Looking for exposure. You see these people wearing respirators and coveralls. That's from a very early study that NIOSH did. I think that's pretty much it. So, questions? That guy's got a real habit, huh? Questions for you guys?
Have you guys studied anything about like the cosmetics or lotions and how those affect health? And then what are the, do you foresee any issues for wastewater and water?
Yeah. So I didn't talk too much about the environmental stuff, okay, but there are a fair number of studies suggesting that some of these nanoparticles released into the environment are going to have adverse effects, okay? And so there's a reason, I don't follow that literature very closely, but there's a reasonably big literature saying that these days. On the other hand, they want to use nanoparticles, they want to disperse nanoparticles in the environment for environmental remediation purposes. So that's, that's a rock in a hard place. So yeah, they want to put carbon nanotubes in tires. All that's going to wash off the roads into the bay, into the rivers, into the lakes. And there have been these documented effects at pretty low concentrations too. So from an environmental perspective, that's a real risk. And remember, a lot of these nanoparticles are not, strictly speaking, regulated as waste. And so corporations and businesses are free to put a lot of them in the garbage. So they're going to go to the landfill, and if they leach out of the landfill, they're going to end up in the rest of the environment. So yeah, there's a lot of those kind of questions out there. And there's no quick moves to come to any real quick conclusions on any of that.
Is there anybody who's studying that?
Oh yeah, there's lots of people studying it. Yeah. If you go on PubMed, you can pull up a lot of those articles. There's a lot of places where you can read about this. So the EPA has a whole website on nanotechnology stuff that they're doing. Those are all very good questions. Question?
Is there any way for the consumer to know
Well, the answer is it depends. So when you're printing with your inkjet printer, you're printing with nanoscale ink particles. Okay, at least a lot of them do. You don't know that. It doesn't say that anywhere on the package. In fact, they're doing everything they can, that industry, not to say that. Okay? Because they've been using nanoparticles and inks for years and years and years. And they don't want anybody to think it's now all of a sudden bad. On the other hand, a lot of nano-enabled products, they trumpet the nanoness of it. Because that's the thing that's going to make you buy it. That's why my kid wanted that nano bat, that carbon nanotube bat. Because, it's got carbon nanotubes, Dad. That's better than the carbon fiber that they made last year.
But I imagine it's a little different when you're applying it to your skin versus just hitting a baseball.
Yeah, so cosmetics are a big scale use of nanoparticles now, and there has been a little bit of research on that. I haven't followed that literature very closely, but you can imagine if you're using with powdered cosmetics, and certainly the sunscreens. Now, there have been a fair amount of studies of sunscreens. And if there's adverse health effects to that, it's not all that obvious. In other words, it's not clear that that's any kind of a problem at this time, at least for you. Of course, you take a shower, and now it all runs off into the drain, and the drain goes to the water treatment plant. Is there maybe a problem there? Is there a problem when it gets dumped out into the bay? Those are questions that are less clear. I think I'm pretty comfortable putting on nanoparticle sunscreen, so I don't have that problem, except for the spray-on sunscreen that contains nanoparticles. Yeah.
They published a study on drinking water treatment with titanium dioxide and sunscreen use, and they talk about that.
Is that right? Yeah, there's a lot of studies out there. When I started this back in 2005, I read every article that was ever published. Now, of course, that's totally impossible to do that. But it was so nice to be completely on top of the literature for 2 or 3 years. Because I had read every single one that could be found. But those days are long gone. Tremendous amount of nanotoxicology research coming out of China these days. I don't know if I count the numbers, but in terms of volume of papers, they might lead the world. I'm not convinced that, a lot of it's very simple research. And I'm a strong believer that simple research is not necessarily going to get us to the right answer. So these are cell culture type studies, or even cell-free studies. I went to a conference in Zurich, my only international conference I ever went to. And the Europeans are saying they are not willing to pay for whole animal lifetime toxicity studies, big, expensive animal studies. And so they're desperately scrambling to develop complex in vitro models where they maybe get these cells to grow some sort of tissue-like thing, so it's not just cells, maybe 2 or 3 kinds of cells mixed together. And they try to basically mimic part of the body, and then they expose that to nanoparticles because it's 100 times cheaper and much quicker. So they're really desperate to avoid these big inhalation studies, which pretty much to this point, only the United States is funded, for a lot of it anyway. A lot of stuff coming out of China is very simple in vitro stuff nowadays. Lots of it, but pretty simple stuff.
So the majority of the carbon nanotubes are being manufactured now, like man-made?
Well, as I said, they do occur naturally as well in very low concentrations. So, at some point, your gas-burning stove is producing some amount of carbon nanotubes. But in terms of significant concentrations and production for use in industry and research and all that, those are being made by people. There's a bunch of different ways to make them. But now, things like Bayer and stuff, they're making full industrial capacity reactors to make these things. So big scale. So you've got a whole range of thousands and thousands of these nanoparticles that could be introduced into commerce. Almost no regulations. Organizations that range from the DOE, which treat it all as hazardous waste, to organizations probably don't even think about that. So it's a pretty tough challenge. Now, for you guys going out, if you go to places that are making nanoparticles, okay, the one thing you got to do is protect yourself. Okay, that's really important. I tell the story of the Bay Area Air Quality Management District inspector that wanted to, years ago, wanted to go into an asbestos work area, and she said, "I don't have to wear a respirator." I said, "Well, you don't have to, but you have to get by the guard that I'm going to call in 1 minute to block you from the door." And she didn't know that there was a law requiring her to use respirators. Once she found that out, she was very indignant with the Bay Area Air Quality Management District. And I filed a complaint against them, too. So the bottom line is you guys got to protect yourself if you're going into these sort of settings. And as I said, the usual protections work fine. And, like when I went to one of the factories I went to that are using carbon nanotubes for this government research, I thought they were handling it pretty well. Okay, and NIOSH has there's a lot of NIOSH things you can see online where they show you what factories look like that are doing a good job, and they show you what factories look like that are doing a bad job. Okay, and there are definitely factories that are doing a bad job. I mean, these guys, I talked to these people, and some of my own people, and other people I've met in industry. And they, for example, a lot of these people came out at University of Texas because that's where a lot of this early stuff going on. And the stories I hear is they blew their nose and it came out black when they were working in the laboratory. That kind of thing can't happen anymore, okay? Because that's just not safe. Any other questions? Well, thank you so much for attending. If you want to talk to me, you can always reach me up at Lawrence Berkeley National Lab. I'm in the book, as I say.